Hello, my name is Tristan Tarrant and I am a Principal Software Engineer at Red Hat. This presentation I'll be talking about the changes that we made in the context of the CloudButton project to Infinispan, an open source in-memory data grid project, to enable near zero friction scaling in serverless environments. So the mission that we set out doing was to take this project, Infinispan, which was designed over 10 years ago for a very different landscape, where bare metal deployments were the norm, where users would provision clusters at capacity up front and only add nodes when those the capacity availability was insufficient, as well as and this was done in a manual mode. So we had a number of challenges that we had to overcome to make Infinispan suitable for running in a cloud environment, especially in the context of serverless. So the first one is to reduce the startup time. New nodes should be usable and available as soon as possible. Reduce the impact of cluster reconciliation, so the way that Infinispan does high availability. Lower the memory overhead, the resident set size in memory of each process, each server process, so as to have much higher density and fit more data, and automate scaling. The first aspect we'll look at is how Infinispan balances scaling and availability, as these two things go hand in hand. So Infinispan is an in-memory key value store. It has other characteristics, but this is the one we'll focus on. And it can scale horizontally by just adding new nodes. New nodes are discovered, added to the cluster, and we keep multiple copies of data on the cluster nodes for redundancy, so that in case of a failure, we can always have a backup copy of the data and we can repair the copies. Also, an interesting feature is the fact that we keep read-write latency low by making the clients aware of who owns, which node in the cluster owns the data, so that that data can be accessed in the single hop. The Infinispan implementation is based around a consistent hashing algorithm, which maps keys to nodes. These nodes are called the primary owners. We also replicate copies to other nodes, which are called the backup owners. The entire consistent hash space is divided into segments. The default number is 256. And so keys are assigned to a segment, and that segment is assigned to the node. When nodes are added or removed, there's a rebalancing algorithm that redistributes these segments to the nodes and trying to minimize the change of ownership and the amount of data that needs to be transferred. But the highest, most important priority for this algorithm is to preserve data integrity. And so this means that it will probably do more work than immediately apparent in order to preserve high availability and ensure even distribution across the cluster. The state transfer algorithm in Infinispan has been non-blocking for a very long time now, and clients can continue to transparently read and write data to nodes even while state transfer between the nodes is happening. However, rebalancing has an impact. Big chunks of data need to be transferred across the various nodes, and there's also a fairly high computation load needed to require resource usages and calculating segment sizes, so to determine which ones need to be moved around. I will now just demonstrate the algorithm very quickly. So provision the first node, the clients connect to it and start writing data. Once we reach capacity, we can add a second node. Clients can immediately connect to it, and in the meantime, state transfer happens and rebalancing kicks in, which means that the segments are evenly redistributed between the available nodes. Now, as clients write more data, the two nodes fill out evenly according to the consistent hash algorithm. Once we reach capacity again, we can add another node, and so on. So rebalancing, as I said, is a compromise. Performance is less important than data integrity for this algorithm. And the impact of state transfer on network and CPU can be significant and adds unwanted latency. So one of the approaches to fix this is to pre-provision all the nodes you need for the capacity that you can estimate. This avoids scaling, but obviously that is not a cloud-friendly way to approach the problem, where you want to use the minimum number of hardware that's required by your computation. So let's try and be flexible. Let's try this. When we redesigned new algorithm, we decided to make some compromises. So we introduced a new algorithm which replaces rebalancing. It's optional, and it's called anchored keys. So we decided to relax some of the rules to remove the impact of transferring large volumes of data and calculating where the ownership goes. The first item is don't rebalance at all. Let's transfer as little state as possible between the nodes. So because of the consistent hash algorithm allowed us to be able to determine the ownership of a key and therefore of a segment in O1, we needed a new way to have all the nodes aware of where the locations are. So we do still need to transfer some state, and this is the key location, the address of the node that owns every key in the cluster. But this is hopefully a much smaller data set than the entire set of values. Also, with no rebalancing, we fill a node with data until it reaches capacity. When we add a new node, we add data to the new node. Data is not moved from the existing cluster nodes to the new nodes. So, using the same approach as before, let me demonstrate how anchored keys work. So we have a client send the first node, and we fill the node with data. And we've reached the node's capacity, so we provision a second node. The clients can start connecting to the second node, and in the meantime, keys are transferred. Then we start adding new data. As you see, there was no rebalancing in process. And so on as we add new nodes. So, advantages and disadvantages. So, rebalancing has a high state transfer volume. All nodes need to exchange part of the segments. Obviously not the whole segments, but only the ones that need to move. As I said, however, that has a potentially high cost also in terms of CPU, which can have a high impact during that time on how the clients talk to the server. With anchored keys instead, the impact, the state transfer volume is very low, and also CPU usage is very low. We just need to send all the keys across to the new node, and those keys and locations. Client latency. As I said, because of the consistent hashing algorithm, server nodes can automatically locate the owner, so client latency is always low. Clients connect directly to the primary owner of the data when writing, and can connect to any of the owners, including backups, when reading, so as to balance the load. With anchored keys instead, client latency increases. I've set high. It means that depending, it's using just a round-robin algorithm, and but at most this is actually one extra network hop, because you connect to a server node, and that server node determines who the owner of the data is, and then forwards the request to the actual owner. High availability. Rebalancing obviously has it built in, and currently anchored keys don't have high availability. So loss of a single node can cause data loss. We'll see how that's fixed. So how does this perform? Let's look at the time that's required to perform a state transfer. During state transfer, 1 million key and a total of 2 gigabytes of values, and we have these are 2 kilobyte values. The blue bar shows the rebalancing algorithm taking about 5 seconds, and the anchored keys algorithm taking less than half that, just about 2 seconds. And it does this with a much lower CPU impact. So this is quite a good result. Let's look at how put get throughput is. These are microseconds, and these are 10 concurrent threads accessing a 2-node cluster. And as we can see, the impact is quite low and possibly acceptable compared to the computation that needs to be doing. So obviously anchored key, as I said, has potentially an extra latency hop, but as you can see here, it is not too significant. Obviously, this depends on the load. So let's look at another aspect, and that is startup time and memory footprint. So Infinispan has been implemented in Java, and the JVM is notoriously very fast. It has a very high performance thanks to its just-in-time compiler that can do adaptive optimization at runtime. It has garbage collectors that can scale to terabytes, so it can handle large volumes of data, but it has 2 big penalties. It has large memory overhead and a slow startup time because it needs to compile the classes. So from cold start to high performance, there can be a considerable amount of time. Obviously, this clashes a bit with the requirements of a serverless environment, which needs things to scale and be available quickly. So there's a project called GraalVM, an Oracle Labs project, which has, as part of its components, a new VM called Substrate, which can compile a Java application to a native application, and with only basic minimal dynamic dependencies. This compilation can do ahead of time compilation of Java code to native code, so it removes this part from the runtime. Obviously, the performance ultimately is not as good as the adaptive optimization of the just-in-time compiler, but it's very good. It can do several things like dead code removal, loop unrolling, and so on. And it will improve over time as the project matures. So, what does it mean to bring a traditional Java application to running in ready for Substrate VM and being compiled to native? It means removing runtime reflection as much as possible. Reflection is one of the big offenders in Java performance if it's not done correctly. And so we've done the work to completely remove all initialization of our internal components at startup. So there's no more reflection there. And also, part of the configuration is now opinionated, and it's resolved at runtime. So we only compile the features that we need. Additionally, internal components can be statically initialized, so they're already ready for use as the application starts. We use the Quarkus project to remove some of the boilerplate from doing all of this work. So what does it mean from total memory usage? So I'm going to show the difference between Infinispan running the JVM and Infinispan running natively. This is the amount of megabytes required after the first put operation, from boot to first put. And so, as we can see, the JVM uses just over 430 megabytes for this, and whereas the native application uses just over 150 megabytes, which that's a third of the memory utilization. So all of those extra megabytes are available for storage. Memory is obviously a very precious item in cloud environments. And what does this look like in terms of timing? So how fast can that server start? So the JVM server is the blue bar at the top, and it starts in just under 5 seconds, just under 4.5 seconds. This is time to the first response, so being able to handle a response. This includes a 2-second cluster discovery timeout. So remove those 2 seconds and you still get just under 2.5 seconds. If we look at the orange bar, that's the timing required to start a native server, and that's the first node. So it will still have that timeout, those 2 seconds. But if we start the next native node, it will start in 0.2 seconds, and also subsequent nodes will also start in that time. So that's a very, very significant difference between the two environments. One of the aspects that I mentioned about Infinispan is obviously that it requires someone to provision additional nodes. Traditionally, this has been a manual process. So you configure a new node, install Infinispan on it, and give it the configuration, and it will then form the cluster with the remaining nodes. Obviously, in a cloud environment, Kubernetes is has been the orchestrator, container orchestrator of choice now, prevailing one. And so the concept of having a Kubernetes operator which manages the life cycle of Infinispan clusters. We've developed an operator which can configure and manages Infinispan clusters dynamically. It monitors the memory usage of those clusters, automatically adding nodes to increase capacity. And it can also scale to 0 once there is no data in the cluster. So I think we have solved also one of the items in the mission plan we had at the beginning. Future work. So in the first design of our anchored keys algorithm, we sacrificed high availability. So the next step is to be able to have additional replicas that would allow repairing data in case of node loss in one of the primary owners or the backup owners. We also need to add support to the operator to support Antiaffinity. So that's the ability for Kubernetes operator to provision new Infinispan nodes on distinct, separate physical hardware nodes, so as to avoid the risk of simultaneous node failure caused by the single failure of a hardware node. And leverage the fact that we have multiple high availability nodes to round robin reads to offer more scalability there. Another item we want to work on is the ability to add client intelligence to the anchored keys. So obviously we can't transmit the whole key set to the clients as well, because that would be costly. but we can definitely make sure that the client can send puts to the latest owner, to the last node that's been added to the cluster, so as to remove any additional latency involved there. And gets, obviously, we can't improve any further, and this can continue to be used a round robin approach and be balanced in all of the existing nodes. So we have a number of repositories that were affected by all the work, and I've added a link to the design document of how we've implemented anchored keys. However, many of the changes have happened across all of these projects, so especially changes to regarding the native compilation, removal, reflection, and optimizations to the image, and obviously the Kubernetes operator. Thank you very much.